Welcome to another installment of our highlight videos on recent physics papers. In this talk, Ben discusses the difference between quantum trajectory theory, which describes the behavior of individual quantum particles, and Schrodinger's equation, which statistically describes atomic ensembles. From there, we dive into a paper which uses QTT to describe a way to catch an electron as it jumps between energy levels in a single atom. We'll cover the experimental setup, which uses electromagnetic fields to induce Rabi oscillations in an artificial V-type atom. And then, how the authors derive a method to catch an electron mid-transition and redirect it to a state of their choosing with high probability. This method shows promise for a real-time intervention technique for controlling quantum systems. Okay, so Benji.
Hey, I'm back.
Welcome back,
Finally,
man.
I see you've improved the place. I'm impressed.
Dude, I'm making some changes. I hope they come out nice.
Yeah, we're going to make some real dramatic looking content.
It's going to be dramatic physics.
It's going to be freaking great.
At 60 frames per second.
All right. So, welcome back to Quantum Trajectory Theory, the talk part 3. In particular, right, last time we left off at showing how to derive the Heisenberg uncertainty principle for matter, right? Mm-hmm. And let's just zoom back out for a sec, right? The last two talks, we effectively went through how light and physical matter, right? The history of discovering, oh, it looks like either a wave or a particle, or eventually having to reconcile the idea that it is in fact both of these pieces. And we started this whole talk with the promise that we would understand this graph. In fact, this is just the first piece of what we're going to understand today. So yeah, today we're finally getting to that. We've understood the history of particles, of waves.
1 second. I got it. Tell the AC to shut off before it gets out of control.
Before it gets too noisy. That's
there you
fair.
go. Okay, good to go.
So, right, we established a history of how, we thought about matter and light, and then realized that they are both kind of comprised of the same thing, this wave particle bit. And so now what we get to do is get back to the original view of what this science show kind of was going to be, of like, hey, here's a result from a paper, right? Here's a paper, the cutting edge of science. Let's digest and understand just how cool it is that the knowledge that's coming through from this paper, the things that we've discovered, right? So, in particular, we last time finished, right, went through the process of discovering that on the smallest level, the stuff that makes us up has this dual property, these wavicles, and in fact are just different wavicles with what turns out different spin. Maybe in a talk we'll get to what separates that.
So wavicles.
Yeah.
I don't remember that term.
That's a portmanteau that sometimes is used. It's also terrible.
Oh,
so
okay.
like,
I gotcha.
Don't use it too much.
Okay.
But, if you're looking for, you want to talk about a wave particle, it's like, But when you're, fundamental thing, it is both of these things. So why not make a portmanteau of it? So, once we are dealing with these types of particles, these quantum mechanical particles that are sometimes actually look like particles and sometimes instead look like waves, the theory that we rested upon in order to understand them and predict their behavior, at least as accurately as we possibly could, ended up being quantum mechanics. And one of the interesting things is that quantum mechanics is, clearly it's very different from classical mechanics, but is very different in one thing. It's an ensemble theory. Whereas classical theory will give you an object that you're going to pay attention to, how it moves, what forces can interact with it, and follow its trajectory through that. Quantum mechanics instead focuses on understanding how to predict the connection between the possible states that your quantum particle could be in. It's similar to how statistical mechanics and thermodynamics works, right? Where they are both methods of dealing with systems where the fundamental parts have data that seems to be below what you can monitor, right? A quantum mechanical particle will have some position, have some momentum that when I measure its position, I won't have access to. In theory, it still has it. We just have to deal with the fact that I don't know what it is at the same time. With statistical mechanics, right, I know that, well, I can measure the temperature of this. I can measure its volume. So the things that I have access to, these macroscopic things that I'm trying to predict how they move, right, are readily accessible, but I know fundamentally that this water isn't just one globby object. It is instead made up of many things. So I know that there's data that is hidden below what I can actually get access to. Because even as I make more and more accurate measurements, I know fundamentally it's never going to be possible to come up with an apparatus that tracks the position and momenta of every molecule of water in there.
Wait, no teleporter?
Yeah. Even if they were just classical balls, like if they just acted like perfect everyday billiard balls, with maybe a little bit extra stickiness to account for the fact that it's, a liquid as opposed to a gas. But even if it did that, I would never be able to stick some sort of, mechanical apparatus that would keep track of all of that data all at once. So what we turn to in those cases is ensemble theories, which the way that it works is that you create the collection of all possible ways that I could configure, right, my system. In the case of the water molecules, what I think about is how many ways can I arrange, the trillions upon trillions of atoms that are in this glass, such that, at the end of the day, none of them are outside this volume, that there's an average kinetic motion that matches the temperature, and match it something. We've got volume, we've got energy, and as far as this is concerned, that's all that is going to matter. Now, with statistical mechanics, you have an additional assumption that allows you to, in principle, track, if you knew the microstate, how it would evolve, how a single instance of a system would evolve, and that's the idea of ergodicity. It's the idea that if I can imagine all possible, basically starting configurations of my water, based on based on the temperature and pressure that it's put at, those states all represent all possible states that the water could go as it evolves through time. So the idea is that, okay, if I understand all positions in phase space, I can understand my evolution in time. Because the fundamental thing that we know we can get, at least that StatMech assumes it can get, is that when I'm looking at these systems, even though I don't have access to the information, I know it's there. To the hidden information that's below what I can monitor, right? I know it's there. And so I can imagine the world where it's like, oh, okay, this thing behaves. If I knew the microstate, I could perfectly predict how it would flow through different, other microstates as I change what it's being put into. If, for example, I set it so that it's stuck at a certain temperature, I know that not temperature, a certain energy level, I know that the only microstates it'll visit are all microstates that have exactly that energy. Closely with temperature, although there's a little more spread. You can have a little more fluidity in what that is. Quantum mechanics follows how statistical mechanics treats ensembles, and the ensemble is that collection of all possible, initial starting positions, initial microstates. But quantum mechanics doesn't have the ergodicity assumption. We don't start with knowing that there's basically hidden variables. We don't get to assume that from the beginning. Some people try to attach that on, but that's not part of the vanilla quantum mechanical theory that really we've used to make these initial predictions. And so what that means is, even if I know how if I know my quantum mechanical system, right, and we've covered this a couple of times, where I will only find it in eigenstates of whatever operator I'm measuring, right? So let's say I know the distribution, the probability of selecting, the different eigenstates that I could measure for whatever I'm looking at, position or energy. Energy is usually the best one. When I look at how that will evolve in time, the thing that I am going to get statistics for is the result of doing this many times over many particles. So basically you imagine setting up a large number of these systems, right? Identically placed systems with the distribution that I know it's in to begin with. And I let them all evolve, say 2 seconds. And then I check, what's your energy, right? And the statistics that quantum mechanics predicts for me will reflect the statistics across the entire ensemble that I have. But it doesn't track the behavior of any one individual system as it flows through those possible states. So I have a way of, understanding average behavior, but for single particle systems, for example, right? This is a perfect, the most pointed example of this. I wouldn't be able to, from knowledge of where it was, be able to predict how it would flow through what we'll call the Hamiltonian space, the possible configurations that it could. And what this paper shows evidence for is quantum trajectory theory. And effectively what quantum trajectory theory says is saying that no, we do have an ergodicity principle for quantum mechanical systems. It says that, okay, you can take the statistics of the ensemble, and it does in fact apply to the statistics of the single system. And this was initially hard to bring into the picture and accept because of the idea that a quantum mechanical particle can only occupy discrete places, discrete states, right? We talked about this before, but let's open an example of this, right? One of the easiest ways to go about this is we're going to look at one of the first correct models of the atom. We're going to look at the Bohr model.
Oh boy.
Oh yeah. So Bohr model of the atom, pretty simple. I have some positively charged proton. Let's say this is. Does it feel fuzzy? Let me make this bigger.
It's pretty big, man.
Not bigger. The line thicker.
Oh,
yeah.
Gotcha.
Right. And let's take a helium atom, right? So the basic idea is that I've got positively charged nucleus, right? A single proton. And then I have a negatively charged electron. Wow. Words are hard sometimes, right? This model comes from classical physics. It comes from orbital mechanics, which is that, if I have a source of force, gravity, pulling something in, if it's moving around at a certain velocity, right, there's a stable velocity or a stable orbit radius. Man, I'm really bad at drawing circles, but it's fine. Most people are. Where this atom with its momenta would have, right? And the balancing between the electromagnetic potential pushing in and its kinetic energy defines what this orbit is. Quantum mechanically, since I am only allowed discrete energy levels, what that means is that the orbits around this proton, right, come in discrete possible values, right? And so the question is, I've got my electron, it's in the lowest state possible. And let's say I shoot in a photon, right, of the right energy so that it is absorbed by the electron. And then the electron moves from this orbit over to the next one up. Aha. The question is, what does that transition look like? If there's no, if my atom is only allowed to have discrete values, right, then when I look at it, I should never see it in the in-term value, right? I should never see it in the middle here. Right. Well, what that would mean is, okay, the jump must happen instantaneously. It has to be that way, because otherwise the discreteness of quantum mechanics isn't really real. We just aren't looking hard enough to find it. And this was the initial idea proposed by Bohr. Einstein extended the idea of quantum mechanical jumps, these near instantaneous things, how fast they would have to go, etc. And so a lot of prominent people who were working on it really thought this was how it was. Schrodinger, guy from Schrodinger's equations, the guy who tells us, whose equation tells us how quantum mechanical systems should evolve, says, no, this is terrible. No, look at my equation. It is a continuous, deterministic, a deterministic equation, partial differential equation, right? And so he thought, no, it cannot be this way. And it remained a source of debate between the two groups who were trying to argue and understand how quantum transitions could happen. It remained in debate for 70 years until it was seen in experiment. So we saw transitions between what we were able to do is observe, single atom systems and check and try and resolve, okay, where are you in the energy? How do you transition as you go? And as time resolved, as we tried and could get, all we could find was, okay, discrete transitions. So you take a picture of the atom, you go, oh, okay, I see it in the lowest. Oh, now I see it in the highest. Now I see it in the lowest. I see it in the highest. Right? I never saw, the electron in the middle. So the question then says, okay, is that experimental evidence, right? Seeing it in these discrete spaces, which we knew quantum mechanically would have. Is that the end of the story? Well, this paper and quantum trajectory theory says no. You can find the continuity if you look at it the right way. And if you're looking at just the results of measurements, it's not quite the right way. Actually, no, you can just look at the results of measurements. You just have to look at them the right way. Let me just keep saying the same thing again and again. All right, so let's walk through this paper and show that, in fact, how quantum trajectory theory supports what Schrodinger wanted, that the evolution of these systems through their possible states are, in fact, smooth and continuous. All right, so first thing what we're going to do is we are going to look at the experimental setup that the paper authors provide. First up, here's what we have. We have a system in the center here. Let me highlight this. The quantum mechanical system that we're interested in is this guy here. It is an artificial atom. And basically this just is an experimental technique to make something that has the energy structure of an atom. Basically, you can take a small piece of superconductor and give it what's called a V-shaped potential. What is a V-shaped potential, you ask? Well, it's this. Let me get the proportions right. It's this guy here. So this atom naturally has a ground state, right? The lowest possible level of energy, which would kind of correspond to, the Bohr atom. We would have the lowest possible rotational energy, the lowest possible, orbit around the center of the atom. Same thing here. We have a lowest possible energy. There are then two energies that the atom is capable of transitioning to most prominently, right? First up is a higher energy bright state and a slightly low energy, but still higher than the ground state, dark state, okay? And the reason that they are labeled this way is because that's, we're going to be getting information from the bright state. We're going to be monitoring that. And while we won't actually be looking at the dark state, measuring the bright state will in fact give us information on what's happening. So back to the overall setup. What you have is, around this system is a giant electromagnetically driven cavity, and that helps stimulate the system. Because one of the things that 2- and 3-state systems like this strongly go through is something called the Raby cycle, which is if I nudge at the right frequency with the right force, you can drive it and force how to send it from the ground state up to one of the other, either the bright state or the dark state. And the frequency that the system will accept, the frequency that is needed to push the ground state either to the bright state or to the dark state are slightly different, right? They're attached to how much energy does it take to jump in that, that gap in energy. Now, the way that this is going to work is that the information on the bright state is going to be connected and effectively fed into an FPGA, a field programmable gate array, basically a customizable chip. And this is just going to make making measurements easier because it's going to be able to do it quickly. Instead of having to stop the experiment, look at the readout and do this, it's just like, no, here's this chip that automatically does all that stuff for us. And we'll get into the role of that. But the key part is that cavity that drives the system. And in the center of that cavity, you have your actual artificial atom that has that V-shaped structure of energy levels.
The atom itself is supercooled?
Yes.
Okay.
Yes. First off, you need to make your material a superconductor. So obviously, it's going to be really cold, and then for the millikelvin, the paper mentions why millikelvin is particularly useful for that. For this particular artificial element, it's a technical detail, but yeah, you need it super cooled down in order to see superconducting in this particular thing, and in order to make sure that the superconductor has that energy structure there, right? There are energy values that are far above the bright and the dark, right? There's no way to fully limit it to an actual two-state system, particularly with an artificial atom here. And that will fiddle with the data a little bit, but by and large, the thing that we're going to be interested in are these three states here. So how does this thing work? Well, effectively, when you have a multi-layer structure like this, you can run all right, so if I just had the ground and the bright state, right, what I could do is I could stimulate it with electromagnetic energy. And so my probability of finding it in either the excited state or the ground state would depend on the frequency, like the amount that I poke it at. And there's a frequency that corresponds to the energy gap between, two states. That is your resonant frequency for that energy jump. So if I run the system and I stimulate it at the resonant frequency for the bright state, then the likelihood that I find it in the bright state at time equals 0, right when I look at it, right when I start the drive, is spiked. It is very high and very low around finding the ground state energy. Same thing with the dark, right? I can run the ground to dark frequency in the same way, but I can also run them at the same time. And so what happens is the transition from bright back down to ground will emit photons, right? That is what we are measuring. In effect,
so what do you mean you can run them at the same time?
You can, because what you can do is you can have a superposition of the two, basically you have it stimulated by two different forces. You are stimulating it both at the frequency, with one force at the frequency of the ground to bright state and at another frequency of the ground to dark state.
So you have two input signals?
Mm-hmm.
Okay.
Effectively. What that will...
Or is it just one wave that's got both frequencies?
With superposition, the distinguishment is trivial. As far as the math goes,
right.
You can't really tell the difference, right? Which is the whole point. So what this ends up acting like is like a little LC circuit where and what's interesting is that this LC circuit, effectively this acts like an LC circuit. And so if the system is in the ground state and bouncing back and forth between the ground and bright state, and an important distinction, you aren't driving the system in a way that links your bright and dark states. So you never see any transitions between the bright state and the dark state. That's an important thing.
Okay, so there's not a little sub-frequency that could possibly lead to either excited state that you're running it at.
You have set this up so that only transitions between ground and bright and ground and dark states are possible.
Okay.
And what that means is that it effectively runs like an LC circuit where there's a frequency for, right, this circuit here, if it's going between the ground and the dark state of a particular, here inductor and capacitance equivalence. And what will happen in the system we'll see is that occasionally it'll shift. Instead of bouncing between bright and dark or bright and ground, it'll go between ground and dark. And that's like changing the length of your inductor. So your frequency, the natural frequency, the resonant frequency of this LC circuit changes. So that's how we can tell, that's how this apparatus is measuring which state is in what. So basically what we're doing is we're saying, okay, here's this LC circuit. Let's check how many photons are in the chamber at a frequency here given of kappa omega or kappa gamma. The chamber itself has a natural resonant frequency. If I didn't have the artificial atom there at all, it has a natural frequency of photons in it of 8,900, basically 9,000 megahertz. And what's interesting is when I put the artificial atom in there, it changes the resonant frequency of the chamber, the cavity itself. So that's how we're able to, measure basically which state it's in, because the artificial atom, the state of the artificial atom changes how the resonant frequency responds.
Now, is this just what it intuitively sounds like? The cavity is actually set up to just allow a 9 gigahertz standing wave to just sit there, and then as soon as you put something in there, you're basically
I believe
breaking
so.
it.
As far as the paper, what the paper goes into, yes.
Okay.
So now, So what that means is, and this is actual interesting response. What this means is that come on, let me import. There we go. This thing is doing annoying stuff. Oop. That's not what I wanted to do. Is that the way the cavity's harmonic frequency responds is shifted based on these two parameters, chi B, chi D. So chi B is about a 5 megahertz shift. So that's how much the resonant frequency of the cavity changes when the artificial atom is in the bright state. And the chi D is how much does it change when it's in the dark state. And chi D is a change of about negative 0.3. So the difference between the bright state shift and the dark state shift is very large. Right? And this is basically in reference to the ground state. So if I force the atom to be in the ground state, this is its natural resonant frequency. When it happens to be in the bright state, it shifts the frequency to a 5 megahertz shift. And when it goes to dark, it's a 0.3. It's 1/10 the difference, right, between ground and bright is dark. So what this means is that this sets up a really strong way to know whether the system is in the bright state or not, but at the same time tell you practically nothing about whether it's in the ground state or the dark state. And you can see that by just how much the Gaussians for the gray Gaussian and the red Gaussian overlap, right? They're really tight. And if I, have my data, I sample and effectively get a measurement somewhere in the middle, you really can't be sure, right, whether it's coming from a shift from the ground state or whether it's coming from a shift from the dark state, right?
So is chi the susceptibility, the electrical susceptibility?
No, not in this case. This is just a parameter that is the shift in the resonant frequency of the cavity, right? So what this effectively, right, when you're driving at a certain frequency, what this effectively ends up being is how many photons are in the cavity at a certain time, based on the state that the artificial atom is in. So And what's interesting is even though I'm like doing it this way, it still gives me access to understanding and having a good guess of when the system is in the dark state, because while also still protecting the ground dark state from actually being collapsed upon, right? Wave function collapses. I actually measure the thing. Why? Well, it's protected by that V-shaped structure, and I'm not setting up in any way through this method to check on whether to distinguish between ground and dark with high resolution. And the drive between ground and bright is much faster and much stronger than the drive between ground and dark. And I'm constantly, quickly checking on the state of the system of whether it's in B or not. Right. So when I collapse the wave function asking, are you in B or are you not in B? Right. If it's in B, yeah, okay, I've perfectly stuck it. I've perfectly stuck my quantum mechanical system there. If it's not in B, well, it's still a question of, okay, if it's not in B, it could be in ground or dark, right? So there's still some quantum superposition that exists, right, for those two states, because I haven't asked which one of those two it is. Basically, the key is that you just need to make sure that your gamma, right, the rate at which you monitor whether it's in B or not, is much, much faster than the frequency that you're driving, that is the resonant frequency between ground and bright, which will be much, much greater than the resonant frequency between ground and dark. That's what you kind of need to set up. And
So it was chosen on purpose to have dark and ground be so close to each other.
Exactly.
So that there would always be this uncertainty as to which one, so that you're never actually collapsing the wave function by knowing which one it is.
When you're measuring it through this method. Now, eventually later on, we'll get to measuring and distinguishing, are you in dark or are you in ground? Because that is the ultimate question that we are trying to answer. The ground and dark transition corresponds to the transition of the Bohr model between, the lowest and when we hit it with the photon and it jumps up. We want to understand what is the nature of that transition. How does the quantum mechanical system go from being in the ground state to the dark state? Is it instantaneous? Is it truly instantaneous, or is it some continuous process? Mm-hmm. And since we are monitoring this particular setup continuously, what we can say is, these are single particle interactions. So even if I do have to construct the whole behavior from an ensemble of measurements that I've made, I'm still understanding the behavior of a single particle, right? Of a single quantum state. Does that make sense?
Okay.
Or in this case, a single artificial atom, right? We've made it that this thing acts like a single particle system. And right, that was the question of how do you deal with those in an ensemble theory. And that's the idea of quantum trajectory theory coming in. So what I do is I let this experiment run. I have my artificial atom in the cavity. I run it. I run a wave that is strongly driving it between the ground and the bright state, and another superposition between that and a weak drive that runs between ground and dark. And the FPGA is going to be at a much higher frequency than either of those drives, be checking, effectively, how many photons do I see in the system, right? Because that corresponds to a drop from 5 photons will correspond to a drop from the bright state down to the ground state. And interestingly enough, on average about 0 photons. It's like 1 photon every 5 transitions is what corresponds to a dark ground state transition. It's very, very slow. It doesn't happen very often, and it's very weak population. Okay, so the results of this experiment when you run are this bad boy, this thing that I promised to explain right at the beginning of this. So let's go ahead and explain this graph here. You have the On the bottom, you have the regulated Q required between that, basically raw data from the FPGA. Then you translate that into square root of a number of photons, just because of the easiness. So the FPGA, what it will output is telling you, oh, okay, this peak here of when I measure the number of photons, I'm going to guess that that is corresponding to the bright state, right? Blue here on the dots, blue here on the thing, on this guy here, right? Okay. So what do I see when I look at this data? Let me make sure that actually, let's shift this up so that my computer is not in the way and we can look nicely at all of this. The thing that I want to pay most attention to is that this centerpiece here in the middle, where I have the system is running and jumping back and forth between bright and ground states, just like what I would expect it to strongly drive. Now, at a undetermined position in time, for this experimental data, and this is what the authors say is a typical example of what the data will look like. Okay. So at some time here, it's about 35 microseconds into the data. What happens is that the emissions of photon suddenly rapidly stops and stays quiet. Okay. Now the FPGA is right, because the system is constantly going between bright state and ground state. There's going to be some time where it isn't when it checks and there's no photons in there, right? There are no clicks, we'll call them. So the FPGA is programmed with a certain amount of time to go, well, maybe it's not in the dark state yet. It could still be in the ground state. And so it'll check again and check again and check again. And so there's a time, T catch, which we'll get to why it's called catch later, where I think
it's pretty clear, actually.
Yeah, where it says, oh, wait, okay. After that, I still don't see any photons. Oh, you're probably stuck in the dark state now, because the dark can't transition to the bright state. It can't emit any photons in that way, so I can't get any clicks. And it stays in the dark state for a little while, and then eventually, bam, I start seeing bright state again. So somewhere in there, it must have transitioned back to ground and then back up to bright state. And then we'll go back and forth between bright and ground, bright and ground, bright and ground, bright and ground until some other position.
And these are random intervals that these T-catches occur at, right?
Yeah.
Okay.
Yes. And actually, that's what the next picture will show. Okay. Right. Which is that the next interval that pops up, right, will have basically the same thing. There is a drop in the number of clicks that I see, and that continues. And that continues. And eventually we go, well, it must be that it's stuck in the ground, it's stuck in the dark state. It must be that way. And then eventually it'll transition out of the dark state, clearly back to ground, and then back up to bright. And we'll start seeing photon clicks again, photon registers. So there's a little bit past 200 microseconds that's interesting, where you actually see a response of more photons than what you should see for the bright state. And that's going to be the evidence and the occurrence of those higher energy states we were talking about. So what you can see is, I expect, for this QREC, I expect between square root of 2 and negative square root of 2. And here I get stuff that's well above that point. But even across this sample of about 600 microseconds, which is pretty long for the data they have in this experiment, right? The amount of time that it spends in the higher energy states is pretty low. So we don't have to worry too much, which confirms our idea that when we've constructed this artificial atom, the thing that we really should pay attention to mostly is ground state, bright state, dark energy, or dark state. Dark energy plays matter in atomic roles, definitely.
Explain to me why there's a bifurcation, why the y-axis goes from square root of 5 counts to 0, and then up to square root of 2, and then up or down to negative square root of 2?
It's, I believe, a measurement of like the voltage response that they have in there. The paper doesn't go into deep details about the readouts that you get aside from the photon count. The square roots are a function of trying to reproduce the actual, like, a measurement on wave function as opposed to results, because wave function, Bohr rule, you always square it. So in here we take the square root.
Right.
As far as
I'm more wondering why it goes down to 0 and then back up along the same axis. It's like there's two separate graphs here.
there are two separate graphs here.
Okay.
But yeah, these are two different measurements.
Okay, so which one
Readings.
is the one on the bottom and which is the one on the top?
This up here is what effectively maps to the number of photons. This, I believe, is raw data from the FPGA.
Okay.
That they don't assign too much physical meaning to beyond pointing out, oh, okay, this artifact here is from higher energy states. The paper doesn't deal too much with that because it's not physically relevant for what we're understanding here. Make sense?
Okay, and then the bottom one?
Yeah. Hmm?
So what is the bottom one though?
This one here. Oh, are you talking about this graph here?
Yeah, there's two graphs here with two scales.
Yeah. Sorry. So this top. So there's three graphs then. Yeah. You've got this, which registers count.
What are you pointing at?
The DN, this DN scale, which is just saying, oh, okay, here I've got
I don't see where you're pointing.
Oh, you're right. I'm pressing on the wrong thing. All right. I have this graph,
Right.
this graph. Right. This is specific instances of the FPGA saying, oh, okay, I've got a count result. And these are all the arrows kind of represent a clustering of that.
So that's just the detector going click when it detects a photon.
Correct. Here I've got the number of photons that the FPGA that you calculate that the FPGA saw, and then here I've got raw data from FPGA.
Okay, so the middle one is the
physically relevant.
Okay, the one that they've normalized or
right.
Okay,
scaled properly processed.
Okay,
they leave this in because they want to point out this feature because that is most readily seen with.
I see.
Most readily seeing the high energy, the stuff that will have an effect later on, a little bit, but isn't the main part of that. And so you were asking actually very importantly, like, is there a regular interval between this, or is it just random? And the answer is yes. And you can see that very quickly by.
So it's not random.
It's not quite random, but it is random.
Okay.
It's random as if you were running two different frequencies, right? So if I didn't have the bright dark, this histogram is over 3.2 seconds, so a massive amount of measurement of this type of apparatus. And so what it's asking is, oh, okay, if I have this setup, let's imagine that I don't have the dark ground state Rabi drive going, right? What would this look like? Well, what that would look like is if this blue curve continued down like this. That would be the way that the Gaussian would look, and that's what the histogram would be. It would be, oh, okay, if I want to know, if I'm checking how long on average the system is not in B, oh, okay, when I check my system, okay, after long, after a certain amount of time, right, 10 to the, or no, excuse me, if I'm asking, okay, how many gaps do I find where my system is in the bright state or not the bright state? And I say, okay, the thing that I'm going to look is how often is it not in the bright state? The sequential measurements that I make that it's not in the bright state are going to be matched along this x-axis here, right? So, if I've got a certain frequency of, 9 nanoseconds or something, right? Every 9 nanoseconds I check, then if I see two state, I check and check again, and both of them are not in B, right? That will measure to something like here. If I do 3 in a row, that'll measure to something like here, right? Where the string along on average, or the string of data points that I can look in that 3.2 seconds and go, oh, okay, there was a set of gray dots 1 second in length. That counts as one count. And then I, look through for all of those and I put those in, right, and make a histogram out of that. And the histogram that I would expect with a single drive, right, would be this large, just effectively what looks like a parabola opening down. Since this is in log scale, that means this is a Gaussian distribution. When I have the dark state, right, if I just had the dark state by itself, I would expect something kind of like this. Actually, let me make it red. Something kind of like that. And since, what I see is this actual data, this corresponds to just the superposition of those two drives running at the same time.
Right.
Right. So what that effectively means is that the transition points, right, when these occur is random, but it's random around some average that we can tell, right? And that average is defined by the drive between the ground and the dark state.
Okay, so what is random and what is not random then?
So currently what we have is that I know that at random times the artificial atom will go between the ground and the dark state. But if I look at the whole occurrences of when that happens, it is random, but it's random around a Gaussian distribution.
Okay.
Right. So I can talk about the average time that it happens, right? You're very unlikely to see a gap between transitions between ground and dark state that last an eternity, right?
Okay, so it's basically stochastic.
Right. Yes.
Okay.
That is random.
Okay.
Anytime
stochastic along a Gaussian.
Yes.
Yeah.
Anytime you talk to a mathematician or physicist about randomness, they are talking about stochastic randomness.
Okay.
Yes.
Okay.
Yes. Because if we have truly no hold on what you could get, right, then there's no hope of doing any type of mathematics on that. You have to have I assume it comes from some type of distribution. In this case, it ends up being Gaussian.
Okay, so to be clear, what we're saying is that if I sample any particular time, it's going to be anywhere along this Gaussian curve. But if I do it a long time and I plot all of them, I'm just going to get a full Gaussian.
Right.
Okay.
Right.
So the individual measurements are random, but the ensemble behavior is predictable.
Exactly.
Right.
And that is what the end result of quantum mechanics is, right? The table at the end of the day is very predictable. There's no fuzziness about a table, right? Because the average of everything is so tightly, or rather, the behavior of this table is, because of the number of particles, so tightly bound to that average. Right? So even according to quantum mechanics, if I look at this under the tightest microscope, that I will see random behavior. Once I scale up, it's there. The table is there. There's nothing missing. Okay. So, having let it run, what I've confirmed is that, I do see these random transitions between the states of this artificial atom, just like what I would expect for a single actual atom, right? The occurrences happen randomly, but according to some Gaussian distribution for both the bright and the dark states. And my FPGA can give me pretty quickly an idea of when the system is in a darker ground state, or when it's in a bright state, right? So I can have a good guess of when that should show up. So now what we're going to do is we are going to try to reconstruct the flight, the quantum mechanical particle, as it goes between ground and dark.
So are we going to be interpolating here?
So here's what you do, right? And this is going to be represented nicely by a picture, right? We had that time t catch, right? So what is that? What will happen is I prepare my system so that it's, in the bright state. I've got it bouncing back and forth between bright and ground state. And if I look at this bottom row, right, I've got D, and T, right? So basically when I'm registering counts. When I stop registering counts, if it lasts long enough, defined by T catch, I'm trying to catch when in theory, trying to catch when the quantum particle is going from ground state to dark state. Because interestingly enough, quantum trajectory theory predicts that there is a lag that happens before the jump really happens, right? That there is some time that you could stop the system from making that transition, even though it's about to.
So it's longer than the Planck time.
Yeah. Yes.
Okay.
Quite a bit longer, actually.
Right.
An analogy here to what we kind of have set up is, we're going to try for a bad analogy. Let's go. So imagine you're sitting down and you got a cat sitting next to you. You want to know the state of the cat. And let's say you've got one of those like feather toys that you're moving back and forth real fast, causing the cat's head to move back and forth real quickly. Now, you're not looking at the cat, but what you do have is you have a motion detector pointed directly at the cat that's telling you whether the cat's head is moving or not, right? Now, let's say in addition to this feather toy that you're driving the cat's head at, you've also got a little mouse toy that occasionally you send across the floor. Right? You've got like a little button and it runs across the floor. And when the cat sees that, right, it will turn its head, follow the mouse. And seeing that the mouse is along the ground and much more, juicy and ready to like actually get, it's not some fluttery feather. It's right there and ready for it to pounce on. The cat's going to turn, and sometimes will turn to that mouse, stop moving its head, ready, and pounce, and move from where it was next to you over to where the mouse ended up. These are going to kind of correlate to bright state back and forth and ground and dark state. Here's what we're saying is that if I pay attention to the motion detector, when it tells me the cat's head is moving, there is a period where if I move fast enough and just put my hand down, I can put my hand on the cat right as it's, how when they're about to pounce, they have that tensing moment, right? They're getting all the muscles ready to fire so they can move quickly.
Murder mode.
Exactly, predator mode. If I put my hand down real quick and do it the right way, I can put my hand on the cat and stick it and keep it in the ground state. Or I could also potentially pat it on the butt and make it jump even faster. That's kind of the analogy that we have going on here. And here's how it's going to construct, is that...
So you could actually make a transition to the dark state even faster?
Yeah, this is what we're going to get to.
Okay. So analogy's going pretty well so far.
Yeah.
Not bad.
Yeah. I shout out to a friend or two who I tried this out before while explaining to before. I'm just like, to be fair, I thought that up relatively on the fly and went, oh yeah, that actually works. Let me just smooth it out.
Time to put Schrodinger's cat to good use.
Exactly. Fun fact, we will in fact use this same thing in another later talk. I have plenty of ideas. So what's going to happen is you're going to monitor, the counts. You're looking at that motion detector and going, okay, when it turns off, it could be that the cat, was just resting in between, looking ahead, or is it actually about to pounce? And so I'm going to change the amount of time that I consider as safe to not act, right? That T catch will extend. And once the system has gone through T catch, I stop all driving. I don't move the mouse. I don't move the feather. Everything that would...
You just let it evolve from that point.
Everything that would cause the system to change, I stop. So basically that'll freeze the probabilities that it's at. It doesn't have any more dynamics at that moment. And then I perform a tomography, basically a measurement that lets me distinguish between and ask, are you in D or are you in ground, right? And the results of that are going to be either -1 or +1, right? Since this is a two-state system, this very much is like the spin states of an electron. If I'm measuring like what's your spin in the x or z direction, right? If I have my Stern-Gerlach oriented that way. We've talked about that before. Now, in addition, what you see on here is there's also T on, T off and we'll get to that in just a second. So, as a function of changing T catch, right, I will turn off the machine and ask, okay, are you in D or are you in ground or are you in the dark state? The results that we get, or that the authors get, is this one first. So there are three things here, and we're going to have to explain them all. It's not too bad. So Z ground dark, ZGD, is just the results of that measurement, where I'm asking, are you purely in the ground state or are you purely in the dark state? Now, as I made the analogy, since this is a two-state system, it's just like the spin states. I can also have partial mixes of those that correspond to two different types of superposition, singlet and triplet states, I believe. So this is effectively like the yellow curve and the green curve are asking, okay, what is the x position that you have? What is the y position? What is the y component of your spin? What is the x component of your spin for a spin state system? They're not terribly relevant aside from, I would expect the x position once things have settled to zero, but this exists because I still have the fighting between the two Rabi drives of the bright ground and the dark ground. So even though the system can't transition from dark to bright, it still does have an effect, that drive between bright and ground.
So that's actually measurable?
Yeah.
So you're basically saying this is in defiance of what we would learn in undergrad, where I can hit that thing with a photon all day and nothing's going to happen. Well, actually, what is happening is there's something that's measurable that's happening.
So this kind of comes down to interactions between the possible superpositions you have and the fact that there are higher energy transitions that pop out. Because what you'll also notice is that red line, even though actually, the results of the experiment are the dots. We'll get to the lines later. But even though I would expect to be able to find my system stuck in the dark state, right? The maximum level that Z ever gets to is about 0.9, no matter how I change T on or off. We'll get into that in a sec. And that is a result of the fact that the system has those higher energy states. And yes, in kind of clarification of what we learn in undergrad, right? Even though I'm only driving this system to be between the bright ground and the bright dark, it's still possible for my system to excite up to those higher energy levels. So even if I were to only drive the system at the bright ground frequency, there is a non-zero effect on the dark ground transition, not dark bright, dark ground, that you would be able to see. Like if I put the system, right, and just had, instead of the V-shaped system, just had a ground and a dark energy state, and then ran it at the frequency as if I were pushing the bright, I would still see not exactly the distribution of states if I didn't have that oscillatory force influence running on it. So basically, you can see that the system is being affected by something beyond no influence, even though the transition and the frequency that's being driven at is a bit beyond the resonant frequency itself.
A bit beyond, but not below. It's a bit beyond?
Yes.
Okay.
I believe
okay.
so.
Okay.
Right.
I'm getting eyebrows.
Yeah. So the paper here kind of mixes metaphors on what it's using as transition is like whether it's like specifically being driven by photons or whether what type of electromagnetic stimulation, but the end result is that you never have just these sharp transitions. Kind of like how if you don't have a truly, like if you remember, one of the classic examples of quantum mechanics is the infinite square well.
Mhm.
Even if the moment I take it away from being infinite potential walls and just a very, very deep hole, I will never have zero likelihood of finding the particle outside the box. There will be a little bit of likelihood that even though it's really strong and really powerful, if it's not infinite, there's some chance that the particle just kind of gets out. Kind of the same thing here, I believe.
Okay.
Right? So,
Well, these pulses will also have a width to them, so
that's also true.
So you have a chance to excite to different states, and it also depends on your detuning frequency.
Billy is absolutely correct. And that's, this is the story of the theorist versus the experimentalist. The important thing, like one of the important things in general with science is that, we have a limit on the precision that we can have. Right. So even if I get I send a pulse and it's like, here's the frequency, you're never actually sure that it's entirely that frequency. It could be a little bit, up, a little bit down. There's a width to it.
Right.
I believe actually, I think you would know better, Billy, being the optics person, that even if you knew that like with down, you would still have some amount of pulse beyond just precision. Either way.
Well, I think you have to get into really high frequency lasers to get that short of a pulse width, and that carries its own challenges.
Yeah, that makes sense.
But I would like to point out that basically with this V-level system, what you're doing is you're creating an interaction between the dark state and the bright state where one would not naturally exist by introducing these two fields to link them through the ground state.
Yeah.
So you're creating kind of a circuit between the two, and a long route to get between dark and bright.
Okay,
Right.
so this is just because you have this superposition of signals.
Yes.
Okay.
Yeah, and so once you turn off one field or the other, it essentially becomes a two-level system again instead of the combined three-level.
Right.
It's like two-level systems that share a ground state.
Okay.
Yeah. So let's look at this picture here. Along the, oh man, I cut that off too sharp. All right. Along the x-axis here is the amount of time that we set for t-catch. So at the very beginning, we say, okay, t-catch is 0. About here, this first tick is t-catch is 2 microseconds. The third tick is about t-catch is 10 microseconds, and then, microsecond, following that linear progression along all the way through. So what you find is, okay, in this region where the t-catch, I'm very sensitive. I say, I stop seeing clicks for a very short second. I know, no, stop very quickly. And when I ask the system, are you in ground or dark in that setting? I'm very much finding that I am in the ground state. I'm at z equals -1. You're pointing down. That means ground state. At this region, past t equals, I believe it's 10 microseconds. What I'm finding is, I've missed the cat. I waited too long. I spent too long questioning whether the motion detector being off meant the cat was changing between.
These are
looking left and
hugely
right.
long time frames.
Yeah. Well, no.
I mean, 10 microseconds. So you're saying that if we take longer than 10 microseconds from the time the t-catch starts to try and interfere, that it'll be too late?
Effectively.
Okay. So that's 9 microseconds. That's a huge time interval.
Yeah. But to the level that we've been able to, transition. So here's an important point, is that those are the average results, right? What I see when I actually look at the data is I will see either a minus or a plus. And what I have to do is, over independent studies, stop. Like all of this data here is over 3.4 times 10 to the 6 experimental runs, right? 1 million different runs, trying to figure out, okay, how do we do this, right? And, you take a certain number of them and you say, okay, the t-catch is going to be 0.2, t-catch is going to be 0.1, right? And that's how you construct these curves. But yeah, the speed at which that change happens is an order of magnitude faster than either of the driving frequencies, at least, I believe is what it ends up being. And at the end of the day, that is what really allows for this, this picture, this resolution between Bohr and Schrodinger's views of quantum jumps, is that this jump, even though it's about 8 microseconds, which in comparison to the Planck scale is quite a bit. Quite a bit.
It's enormous.
Is still very quick compared to how well we can measure these systems, how quickly we can measure these systems generally, or excuse me, the experimental data has looked at these systems, can let you say, oh, okay, not only am I monitoring these states and seeing only discrete results, but when I look at the statistics, the difference between being at the low state and the high state is that quick, right? It requires a lot of technicality to resolve it that quickly, that time frame.
Yeah,
right.
Of course.
And it just hadn't, I believe, been done before on that level. And so one of the things that they do is they want to make sure that the transition from the bottom to the from dark to ground, once it's initiated and stuck in ground, isn't solely pushed through and driven by the Rabi frequency, between ground and dark. And what they do,
Or do they just cut the signal?
And that's actually what we get, the T on to T off. We say, oh, okay, if there's a certain amount of time where, I haven't seen clicks that equals T on, I'm going to turn it off. And then you run a little bit longer to catch up to finish up t-catch, and then you make the measurements. And that's what this graph here is for. That's the difference between whether I have T on and T off. If in this picture, T off is just 0. So the entire time t-catch, you're looking at t-catch, you're questioning whether the cat is about to move or not. You still have, the mouse running back and forth. But at some point, here, if I'm questioning, if I want to make sure that it's, not the mouse dragging the cat along, what I do is I, have the mouse run behind a corner and just stay there. And the cat, being curious, might still try and pounce on the thing, right? The experimental data that they get from doing this is this one here.
It was the mouse was the dark.
Yeah, the mouse
frequency.
is the dark Rabi frequency. Okay. Here we go.
So by turning off the field that couples the dark and the ground, you're basically making it so that any transition from dark to ground is just spontaneous decay instead of driving it back down to the ground.
Exactly.
Right.
That makes sense. And so what they find is effectively the same
So it doesn't
trajectory.
overshoot anymore.
So
it's not overshooting anymore.
Right.
Okay.
Well, so the superposition is no longer overshooting. So this is exactly what we would expect.
Right.
And yeah, the superposition being off, again, a fight between the fact that two Raby cycles are firing. Now, interestingly enough, it's still pretty close. The bright ground Raby cycle is still firing. So you can't, right? So to, again, further clarify that point, if I just had the the drive where the frequency is off the critical transition frequency for ground to dark, it still doesn't have, on average, an overall effect on the system. Make sense?
It still doesn't.
It's the fact that you have a fighting between the two frequencies,
Right.
that causes the XGD to shift. Yeah. But with just one drive, the system acts exactly what I would expect with these. Yeah, on average. Here I actually have the proper timescales on here. Excuse me. Okay, yeah, this is why having the timescales are important. So the jump, instead of 10 microseconds, is about to 7. So you've got about 5 microseconds.
Okay. But it's on the order of microseconds.
Right.
Which is crazy higher than I ever would have thought.
Ah, yeah. Well, that's one of the interesting points that comes from it. So an important neat thing is that this T midpoint for either of them is actually predictable. It follows a function. If I have, let me have white. The T midpoint is going to depend on the 3 things that we have set up in our system. Specifically, it's going to depend on, it is the natural log of the frequency that I drive the bright ground state at squared divided by the frequency I drive the dark ground state at, the frequency I measure the system at, plus 1, and divided by no, not 2 times. Here we go. Divided by the bright ground frequency squared and 2 times the monitoring frequency. So when I know, when I've got my system set up to be driven at the 2 frequencies, the bright ground and the dark ground, and the monitoring frequency that I have, I can predict without ever actually looking at the flight data where the midpoint of the transition will be. Additionally, I can also,
So changing the monitoring frequency could change the actual T catch time?
Mm-hmm. That's the idea.
Even though the system itself, the driving frequencies would remain the same. So just by sampling quicker, I could actually change.
Because remember, when you're sampling, even though you aren't affecting the dark ground superposition, you are affecting the superposition between dark ground and bright, because you're affecting the positioning between between ground and bright. So by monitoring the bright, how I monitor the bright and how often I break the superposition, that bright has, right? I'm going to, when I make those measurements, I'm affecting the system. I'm either putting it in this 2-level system or I'm putting it in this the bright state specifically.
But are we actually changing? If we go back to just a crude Bohr model for a second, if we just assume that electron is literally just jumping to that higher orbit, is it jumping faster as I change that monitoring frequency? Is it covering that distance between those 2 orbits quicker?
The analogy doesn't quite track, because that jump isn't what we're talking about here.
Are you monitoring the bright ground by stimulating emission from that state?
So remember what the data that we showed before. I'm effectively monitoring the bright ground by looking at the number of photons in the chamber. So if it's gone through a bright to ground decay recently, there will be 5 photons, and if it's and when it goes through dark ground, neither transition really has a photon that exists.
Oh, so it's already happened.
Yeah.
At that point.
Yeah. You could do, as the paper points out here, they emphasize the transitions down from bright to ground, but you could also have the transitions from the absorption events emphasized, where it's like, oh, okay, I went from having a back on layer of photons, and then they disappeared. It must have gone from ground to bright. But the
Okay, so if we just fix that analogy, so if we drop from bright to dark, does that actual transition become faster?
I actually don't know. The paper doesn't mention if they did change the frequency gamma throughout this.
Because I'm trying to understand what the implication of gamma is in this equation. Because this would imply to me that the ability to interfere with a quantum jump is determined, which I know that sounds obvious, but the actual mechanics of that jump is affected by the monitoring frequency, which I'm crudely interpreting as, okay, it's going to move even faster. It's going to drop out of that state even faster if I'm monitoring it faster.
Yeah.
And it seems, obviously this is quantum, it's so counterintuitive is the norm, but that seems counterintuitive.
I mean, so the math implies yes, and I think because remember what you're doing when you're driving, when you have Rabi frequencies that you're driving, right? You are pushing the quantum system to effectively bounce back and forth between the two states that it has, right?
You're cycling the population.
Right.
As I monitor and cause wave collapse, like the wave function collapse, I'm effectively doing the same thing, right? I force it to either be stuck in the lower population or the higher state, right? So the two possible interactions, right, whether I'm measuring it or whether I'm affecting it through force, will have an effect on the place that I'm likely to find the system at a particular time.
Right.
Okay. So even though they seem like disparate, different actions, they still have the effect of, in loose terms, fiddling with the wave function. So,
okay.
Well, it seems like there's kind of two things going on here. When you detect, when you sample, you're detecting a photon, you're absorbing it, you're taking it out of the cavity. But the presence of photons in the cavity can stimulate emission from the bright. So you would expect that population to drop down faster if there are more photons of the right frequency in the cavity.
God, I love having an experimentalist on.
What are you talking about?
Okay.
Yeah.
So,
And actually, yeah, she's right. That would be an important point.
So you're taking photons out. That would mean less
When you're measuring,
stimulated emission.
right, when you're measuring, when you're checking the frequency, like, are you in bright state or not? You
Right.
are checking, and
So
those photons are destructively detected because it's a photodetector, and photodetectors just eat up.
So I'm sucking energy out of the system by monitoring quickly.
Yeah.
Okay.
I mean, we're pumping energy in as we're driving this thing. Yeah.
Right.
Yeah.
Okay.
Yeah,
So-
but the energy you put in is driving the population up, and the photons you're taking out are keeping the population from coming back down.
Yes, that's an important distinction thing to pay attention to. Appreciate.
Okay, but that all makes sense. That's clear. I just want to. I'm trying to tie the idea that are we making any claim or statement about the actual speed that a single transition occurs as a result of the monitoring frequency?
Yeah, the ultimate push of this paper is that the flow of the wave function representing this one particle and the energy that it's in follows, even though the individual measurements that I'm making are independent and separate from each other, the flow of that is still, in fact, this continuous and typical trajectory. Typical is the wrong word. It follows the same trajectory each time you have these types of transitions.
At the same velocity?
Yeah.
Regardless of how I'm monitoring it.
That is what it appears from this data, yes.
Okay. So the monitoring frequency is not actually affecting the actual velocity of the transition. And I'm using velocity crudely, implying the Bohr model is... Because I'm just trying to understand, like, we know the Bohr model is not real. It's actually a cloud, and the electron basically just has probabilities of appearing in certain places.
So it depends on what you're representing what the Bohr model is. Because if you're thinking, right, Bohr model directly relates the energy that the electron has, or the energy state of the electron, to its position, but quantum mechanically the position and momentum are a little fuzzy.
Right.
The energy state that it's at is that sharp thing.
Right.
So if you don't think about it as directly relating to the position of the atom, it's like, oh, okay, no, this is actually like.
And I do mean that. I mean the velocity of the energy change.
Right.
Okay. So that is fixed.
Yeah.
Well, we do have an uncertainty relationship between energy and time. So since the energy is so sharply peaked and certain, there is a greater uncertainty in the time.
Yeah.
Right. Okay.
Yeah. So by affecting your certainty in time, which would be changing the frequency that you're monitoring the system at, right? That gamma, you would be peaking or changing where exactly, like what energy the system is at. So that would change, that slope. That would change the slope that this would transition at. So that would also change your midpoint. In effect, yes. I think that this paper, one consequence of this paper is that the speed at which you are monitoring your, what they call the ancilla state, the bright state, is going to affect the way that the trajectory that your particle has through the bright and through the dark and the ground states.
Okay. Because I'm almost like I'm imagining this funny scenario. Like basically, I have a mirror, and I'm stimulating it with one frequency, or I'm stimulating it with another frequency.
Mm-hmm.
And the higher I go in the frequency, the longer I have to choose whether that mirror is going to reflect or not.
I mean, yes, but that's a quantum. That is a thing. That is something that's true of all quantum processes, because the time it takes for a process to happen and the energy at which that process happens are complementary measurements.
Okay.
Exactly the same as position and momenta, right? There's an uncertainty principle between time and energy.
Right.
So that analogy, where like, oh, that feels weird. You're correct, and yes, it does feel weird because quantum is weird.
Well, I'm good as long as I'm understanding the implication correctly.
Yes.
Okay.
All right. So we have a formula based on the three things that define our system here: the polling frequency, and the two driving frequencies. I can pinpoint you where the predicted mid transition is. Now, with that said, I can now, and effectively, this data here kind of shows our point on quantum trajectory, is that as the single particle evolves through time between the ground state and the dark state, low energy and higher energy, that transition is a continuous thing. So basically, the probability of finding it in the ground state versus the dark state shifts, right, from being 100%, almost 100% dark state to almost 100%, 100% dark state to 100% dark state. And as the peaks change, right, from one way to the other, that happens continuously at such a way that the average measurement that I get is this smooth, continuous jump. So even though the particle itself will only ever be found in one state or the other, the averaging, so the effective path that it will take, would be that smooth, continuous path. And so you don't need to have the assumption that the ensemble, right, fully follows that. This connects basically the trajectory of a single particle with the idea of an ensemble over all the possible states that I could have with this.
So the line is basically an interpolation between the measured points?
So the line is the fitting if you use the functions, the functions from quantum trajectory theory, what it predicts you should have.
Okay.
Right. Effectively, for example, the QTT predicts that the Z value between between ground and dark should be equal to some A plus B times a tangent hyperbolic of that time t divided by some tau plus c. Right, so quantum trajectory theory gives you, I've got 4 parameters with which to play with, and you can match those to fit here. The paper specifies that in their supplementary material that they also went through the calculations of, if I have, in theory, a V-shaped symbol, what should the values of A be, tau, and C be, without actually matching the data? And the two agree on the percent level they report. So, less than 10%, which is really good for a theory, right? Because there are other extra world factors, higher energy, and everything else messing with what we would see. So, with that level of understanding of how these, how the single particles transition from one state to the next, we can do something wild. We can send a pulse back, if I pay attention well enough, and try and catch that cat, give it the right instructions and keep it either in the ground state or in the dark state. And so the way that we're going to do that is first we're going to introduce the block sphere real quick. And let's say, which is basically what I would see. This is the arrangement of all the quantum mechanical positions that are possible for a two-level systems, Bell-spin states, right? The Z measurements, right, up or down, ground or dark, or correspond to the top and bottom of this sphere. The singlet spin state contribution, the X is right on this axis, the Y, the antisymmetric one, is over here. What I can do is I can redefine what I consider, superposition effectively, what I consider X measurements and what I consider Y measurements. And if I send the pulse that corresponds to that rotation back to the system, it will respond as I push it, basically say, no, you have these photons. What are you going to do? The angle, right, between the original, what the system is originally at, and what I feed it back actually will have an effect on whether the system moves on or doesn't when it's trying to move into the quantum, right, into the darker ground state. And that's what we're going to see with this graph here. This, right, out of the full possible rotation, taking X from 0 radians, leaving it originally there, all the way to 2 pi radians, what is the likelihood of either seeing it move on to after I send the pulse back to the system? So basically, I should explain what happens, right? You have the system that you're constantly monitoring with the FPGA. When the controller notices, hey, you haven't responded, you haven't sent me photons for the correct amount of time, and here they set T-catch to be the mid-flight, right? So the time that the FPG, the controller, looks at the system and waits to see another emission of photons before it says, you're in the dark state, right? That time is set to exactly the midpoint for the driving frequencies that we have. So this guy right here. So I would expect if I don't do anything, or if I, push the system to be exactly like what it already is, I would expect, there's a 50-50 chance between it moving on to the dark state or being in the ground state. Just like if I were to not do anything to the system. Excuse me. I need to finish up. After the controller notices, you haven't sent me for a photon for a while. Here, have a specific kick in a specific electromagnetic pulse that I send to you, and then it makes the measurement to see how the system responded. So basically, it's like this, but in here, right in this state, I send another pulse, basically, another system thing that would be sent out. And that pulse can correspond to trying to push towards the system being, superimposed like this, or, we'll shift it along this block sphere. It's a...
So you're choosing that phi such that it will either drive that population that's halfway in between either up or down.
Right. So, not terribly important, just important visual to kind of see. The reason we want to think about that is because I want to be able to understand this graph here and this reverse pulse angle. And basically, what I'm saying is, okay, as I push the system before I check, if I want to make sure that the system stays in the ground state, right, I would be interested in this purple curve here, right? So, with what looks like about pi over 2 reverse pulse angle on an average of 80% when I send that pulse to the system after it's not sent me any photons for t catch amount of time. After I send that pulse and then I check, what state are you in? 80% of the time it will be in the ground state. And if I keep moving the angle, the phase angle that I send that pulse at, right, the phase that the pulse will have, if it's 3/4 pi, I can make it very, very unlikely, right, down even past 0.2 time. Even though if I did nothing, it should be 50-50 between the two.
Okay, and this is the pulse that was originally going to excite it, right? If I had left it alone and not modify it, don't adjust the phase angle or whatever.
If I had done nothing and not sent this reverse pulse, I would expect a line directly in the middle. That would be the behavior of this system, right? I would have a 50, basically, if blue represented that it's without any reverse pulse, the likelihood that it's in the dark state, red represented the dark state and then blue represented the ground state, they would align on top of each other exactly like this.
All right.
So basically that population that's in between, if you weren't interfering with it, you would expect just probabilistically half are on their way up and half are on their way down.
Right. I can do the exact opposite, and I can say, oh, okay, let me push it to be in the dark state, and that's that pink curve. And
so we shut off the original pulse, and now we're introducing this phased pulse, right?
Right. Because when you make the tomography, you shut off all of the Rabi drives.
Okay.
Right. And so before the Rabi drive, everything's shut off. You no, here, have a
so
pulse.
So we're in the t-catch space of time.
Oh,
right
this says that the Rabi DG.
Right after t-catch.
This is Rabi DG is on. The graph you're referring to.
What?
Oh yeah. So what
this is
she's
when dark ground is still on, but bright ground is not.
So this is when basically T on is equal to whole T catch. So basically they've left the Rabi drive between dark and ground on the entire time until they make the measurement, just like they would normally do.
And so this is at the initiation of T catch, not at the end.
No, this is at the end of T-catch.
So this is at the end of T-catch.
Yeah, so at the end of T-catch, which is set to, so basically at the end of the midpoint flight. So basically...
Okay, so T-catch is not the time period that elapses that you're calling T-catch. That's not actually when you make the interference.
Exactly.
It's after T-catch.
Right.
Okay.
Yeah, right at the end. Because what you're saying T-catch is, remember, the T-catch is kind of trying to capture that time that it takes the cat to get ready to pounce. And here, it doesn't quite match out because, the transition point that we have set up here is the cat, being halfway flying through the air, but somehow you, I guess, catch the cat midair with your hand.
Okay.
Poor animal.
So you could put the cat down or toss it at the mouse.
Yeah. Right.
You monster.
Exactly. Now, so you might ask, well, okay, maybe just stimulating this hitting it with a reverse pulse would cause it to move one way or the other depending on what pulse you hit it with regardless, right? Just keep hitting it with that pulse or hit it at whenever, and you'll find it in the ground state or the dark state, whichever one you tune it to. And that's what these dark dots are for. If I just stimulate the system with this reverse pulse at random times instead of paying attention to, a t-catch time of photons disappearing and elapsing, the probability that it is in the dark or the ground state is in fact very low. And that's what I expect because of the strong drive between the ground state and the bright state. I would expect it to very often be in the bright state. So if I'm trying to stimulate it when it's, in the bright state, that's not going to have any effect on whether it stays in the bright state or not. And that's exactly what I see in the data. So you have to pay attention, and this means you are actively able to see how that the dynamics of the system, dynamics of the atom going between ground and dark are being reflected by your knowledge, right? Or rather, your knowledge is properly reflected here. If I were...
So you're able to catch these particles that are trying to get to the ground state and saying, no, go back
Right.
to the excited state instead of letting it evolve naturally. You can direct it to do a U-turn.
The important point here is that, right, if I'm looking at this previous data here, is I could be maybe, tricking myself into thinking, oh, this actually is real, and maybe arranging this in a way that it doesn't physically matter. And this just happens to make a nice picture, maybe. And the physical results that I'm intuiting from that don't actually reflect on the system. Because if it were, I wouldn't expect the response from the system. I would expect if I were to see, if somehow I were deceiving myself about the results.
So
that I'm
this is just a sanity check.
Right. Then I would, expect random times to give me the same result. But hitting it with a reverse pulse at random times says, no, you're messing it up. You're not getting that smooth trajectory. You're not influencing that smooth trajectory correctly. So when you think you are going through that transition from ground to dark, you are, in fact, actually going through that transition from ground to dark. You haven't just, deceived yourself. So one last picture, and this one's really cool because I really like. So
As opposed to all the other ones.
yeah. So from that last picture, what we found was the optimal angle to shoot the reverse pulse at to get the system stuck in the ground state. So now the thing that I can change, right, and that was set where t-catch was set to the midpoint, right? Now we choose the optimal angle, and we're going to play with the time that the FPG, right, allows the cavity to be silent before it goes, oh, I should send this reverse pulse. Basically, I change my t-catch time. And the results of that experiment are actually incredible. So the red curve, the open dots and solid dots are the difference between when I have my Rabi drive between dark and ground on or off. So let's just pay attention to the filled in dots. The dynamic is basically the same, it's a little closer. If I never sent the reverse pulse out, that's what this red line shows me. And it says, okay, I'm asking what's the population of the ground state? Well, if I ask the state, ask the atom, whether it's in ground or dark state, the moment I sense that there are no photons in the cavity, well, it's always in the ground state, almost 100%, right? That's what this line here is telling me. As I shift farther and farther without reverse pulses, what I find is that eventually it drops to not quite 0, but about 10% of the time, right? Which effectively is reflecting the results of this graph here, but just kind of flipped, right? We go from 0 pure ground state to, well, not quite pure ground state.
Okay.
Right? The purple is asking, after I've sent the pulse, are you in, ground or dark state? Basically, are you in ground state, right? Because we know we aren't in Well, no, it could be in the bright state as well. And with a high likelihood of success, right, up to like 80% with T-catch, even as I extend the amount of time that T-catch is allowed to drop, I can check and make sure, hey, no, stay in the ground state and be sure, right, with a high certainty of, with a high degree of confidence that I've stuck this system back into the ground state. So like here, right, when I had T equals 9 microseconds, effectively from this last thing, I was already pretty sure that the system was in the dark state.
Mm-hmm.
And so this pulse effectively says, no, go from dark state, go back to ground state. And when I check, are you in ground state? Hey, look, I'm pretty sure it should be in ground state. Yeah. But what's interesting is I maintain not quite the same level of confidence, but maintain a high degree of finding it in the ground state, even as the particle is trying to transition from the ground state to the dark state. Right? So I have, with quantum trajectory theory, an unprecedented amount of control over which state the system is in without looking at the system. Because the important point is when I send these reverse pulses, I'm not checking, right, whether it's in ground or dark yet. And then when I do check, I'm having with a high likelihood agreeing with what I wanted to begin with. And that's impressive, right? Because quantum mechanically, a lot of the stuff we've had to do is hope that the ensemble averages of like, oh, okay, if I push the system to be here, it'll probably be in this location, that reflected reality. But now with QTT, we have much more certain control over the fact that I can influence where my system should be through paying attention to monitoring via ancillary states, right? Monitoring the bright state, which had nothing to do with the connection between ground and dark. If I monitor that third state, I can have a high degree of control over which one of the, bright ground or dark that the system ends up whenever I need to interact with it. And I wouldn't have that, and that's an important point, this graph here, I wouldn't have that if I didn't pay attention to it through that bright ground transition, right? That would, like, sending reverse pulses, just hoping that I push it to the ground state or the dark state, corresponds to those black dots, which, those are at random times. Very low degree of success of getting either result that I want. Because what you'll see, right, there are open dots and dark dots. Those are both the ground and the dark states.
Right.
So I have a very low likelihood of getting either of those states. And if those are the ones that I'm interested in having, that's a bad thing. But if I pay attention to it through this bright state, I have a high degree of likelihood of finding it in the place that I expect it to be. Now, granted, there are higher energy states that can mess with it, right? We don't get 100% efficiency up here. But we do have, above, it looks like 85 or so, which really is quite good.
So this is definitely not a violation of Heisenberg because we are measuring two different things.
Right.
But it is basically allowing us to make an observation of something without affecting it.
Right. It corresponds to something in many fields that's called a weak measurement. It's you can peak a little bit, and as long as you aren't just directly walking up to the system and asking it, where are you, right? It doesn't freeze up and stick to one response or another. If you kind of just flirt out, tease out the ideas, the information you're interested in, you might not be entirely sure about it, but you can be sure enough. Well, you know how to influence
probabilistically confident.
Right.
I think the term for this is a quantum non-demolition measurement.
Yeah. You know what? I have it written in my notes specifically that the dark state is a quantum non-demolition measurement. Where is it? What was the exact? Quantum non is indirectly read out in a quantum non-demolition fashion by those three things, particularly that V-like structure, the strong drive between ground and bright, and the fact that I'm paying a lot of attention to are you in B, are you in B, are you in B. Yeah. And so that's the result of this paper. It provides a way of ultimately saying, yes, quantum particles evolve in a way that is smooth and continuous, just like Schrodinger would expect. It's just that, just like with everything with quantum mechanics, when you measure it, it certainly looks like it's either in one place or the other.
But once again, when you average it over time, over many measurements,
Right.
you get something that looks continuous and
Right.
smooth.
Right.
Okay.
And the point is that here I no longer have to worry about an ensemble of identical systems. I can say, oh no, this is how this one system looks and behaves. Right. And the wave function that it has follows basically the same statistics and functions that I already had for quantum mechanics, right? Just vanilla. But like I said, it's like finally adding to the ensemble the idea that all of this ensemble can map to understanding how one system flows through time. And that's something that had been missing in the original theory.
Okay, so just to be clear, what we've done here is we've said, okay, by monitoring something or making a non-destructive measurement, I can actually interfere with a jump that I'm expecting to happen in the energy state of an atom.
Right.
And the fact that I can actually make a informed decision on how to interfere with it based on that measurement means that it's clearly not happening instantaneously.
Right.
Because there's clearly an amount of time between when I measure and when I do something as a result of that measurement.
Yep.
So we've ruled out the possibility of a truly instantaneous transition.
Correct.
But have we gleaned the actual rate that that transition occurs? Or have we just set an upper and lower bound based on our monitoring frequency?
I mean, as you point out, right, that monitoring frequency, I think does leave wiggle room. Yeah. And ultimately, in order to, understand like the strong line on that, you would have to pump up that monitoring frequency. Now, an important point, right? All of these dots that we saw in all of these graphs, the polling frequency is high enough that the uncertainty in these measurements, right? And actually, I mean, that's kind of really how all the experimental data will work, right? You always have upper and lower measurements. The error bars are smaller than the physical size of the dots here. So they're very sure that like these trajectories are the ones that you're finding. It's not just like, oh, it could be this way or that way. It's like, no, it's very, very finely defined.
Well, you can also design that catch time using the Rabi frequencies. Yeah. The Rabi frequencies are proportional to the strength of the electric fields.
You definitely see that.
So that's the final result on the paper. That ultimately knowledge of the system on this short time scale isn't incompatible with the fact that there is an unpredictable switching behavior, right, on the long time scale. I don't know when on the long term when I'll have these transitions between ground and dark from the bright, really in either of them, right? The only reason that I'm kind of sure about ground and bright is that it just is happening so frequently. If I were to try to monitor on a much slower frequency in order to pick up, whether, to start to have uncertainty on whether it was in bright or ground again.
Okay.
Right. But since that's not what we're paying attention to, we're interested in when does the transition between ground and dark happening? We're using that bright as a third thing. So,
and to be clear, we're not, this experiment is not implying that there's this quasi state that the atom occupies in between.
Right.
We just don't have enough certainty to know when the actual transition occurred.
So, because effectively what we had before is that the experimental data looked like that transitions happened in a way that before the transition, 100% of the time, you would find the atom in its ground energy state, and then after the transition, 100% of the time, it would look like it's in the excited state. And so this is the first time that we say, oh, no, that what looks like a sharp jump, if you make it if you zoom in really tight, oh no, it's just this fast jump that's, on the level of microseconds, which for a level that we've been able to probe
Well,
so
there's
far.
a lag of couples microseconds, right? But we don't actually know what the actual speed. Again, though, the actual velocity between those, that part could still be instantaneous. It's just we know that it doesn't occur instantaneously after we stimulate the particle.
Sure. The probability. Well, okay. So the probability wave, right? The probability of finding the peak of the probability wave has this defined velocity, I guess, following the slope of that curve, effectively. And the important point is, at the end of the day, what we can really extract is we have to kind of treat that probability wave as a real physical thing. So talking about the jump being instantaneous would be to say that, the jump between the peak being at 0 energy and the jump being peak at some energy being instantaneous. That's not correct. We have the smooth transition between the two states, even though when I measure, right, the wave function collapse forces it into one or the other.
Okay.
Right? Does that make sense?
So it's smoothly transitioning, but we could never violate the quantum nature of quantum
Right.
mechanics by stopping it halfway through.
Right.
Okay.
We can never force. So even though I can never see the atom in between the two different states, like when I measure it, it's this or it's that. The probability, the averages that I'll see, will trend smoothly, and this is actually kind of ties back to that.
So what we're doing is manipulating the probability amplitudes of the different states using this reverse pulse.
Right.
We're tweaking those time-dependent constants in front of the states.
What's fun is this actually ties back into that last talk that we did about Merman's paper, right?
Oh, yeah.
The fundamental. It really it's really cool because it seems to fall in line with that. The fundamental amount of information you can get from a quantum mechanical system is that 1 bit. You can either be up or down, 1 bit's worth of information. But the transition between those, as long as I'm not looking, will be continuous.
Okay, so it's just like in a memory chip.
Yeah.
When I set it to 1, the next time I read it, it's going to be 1.
Yeah.
But who knows what's happening in that brief period of time?
That's a fine analogy.
Yeah. Okay.
Yeah. So and with that understanding, and this is always what's cool about science, is that with that understanding of how it works, we're able to have some control about how it will move between those states and how quickly I can be like, no, go back to the ground state. I know you want to go to the dark state. Go back to the ground state. That's really cool.
Indeed.
So this is that paper from Letters to Nature, I believe. Yeah, Nature Letters, and
I think you've got the front page of the paper somewhere buried deep.
yeah, it's this bit
There
here.
it is right there.
Yeah, by Menev et al. Menev, Mundhada, Sankar, many people.
Yes.
Oh goodness, I'm gonna stop before I start mispronouncing too many names. But yeah, Menev et al. And this was a really cool, impressive paper. Just experimental setup being like, no. This cool understanding of quantum mechanics is true.
And this is enabled by our advancement in semiconductors.
Absolutely.
Yeah, I mean, to be able to hit these frequencies reliably.
Yep.
That's pretty impressive.
It's been great. So that is the sequence of stuff on how we can understand quantum trajectories. It's that, the flow of a single particle through the Hamiltonian space that, the states occupy is the same as the ensemble. And that allows us so much more finer control over how quantum mechanics actually behaves.
My takeaway is that cats are a viable analogy for anything in quantum.
So far.
Yeah. Well,
All right,
see
man.
you next
Awesome.
time.
Thank you very much.
Yeah.